In this video, we're going to talk a little bit about, or review a little bit about finding the slope and maybe a little bit about the tangent lines. And in that, I wanted to do this free response question, which will maybe remind you of some other things as well. So, the rate of fuel consumption in gallons per minute recorded during an airplane flight is given by the twice differentiable and strictly increasing function r of time t. The graph of r and a table of selected values of r of t for the time interval from 0 to 90 minutes is shown above. Use the data from the table to find an approximation for r prime. Well, r prime just, of course, is the derivative. It means the slope. So estimating the slope at 45 simply means we're going to look at the points on either side of 45 and find the slope. So difference in y's over difference in x's. So 15 over 10 or 1.5. Now they want us to include units on that. Easy enough. The rate, or this R is actually a rate. So it's gallons per minute. We just found the slope, so it's going to be gallons per minute per minute. Okay, so gallons per minute or gallons per minute squared. Next, it says the rate of fuel consumption is increasing the fastest at time equals 45. What is the value of r double prime? Well, if the rate is increasing at the fastest, that means that r prime is at a max. Well, if r prime is at a maximum, its derivative has to be equal to 0. And explain your reasoning, you would just say, since r prime is at a maximum, r double prime must be 0. And that really goes back to the fact that it is twice differentiable. You know, we're not going to run into any issues with a cusp or corner or something like that. You might want to say that in your answer. You might want to say r prime is at a max, you know, it's 2 times differentiable, something like that, twice differentiable. Approximate the value of the integral from 0 to 90 using a left-hand Riemann sum with 5 subintervals. So left hand, just remember, means we're, you know, if I'm going to draw on the picture here, we're going to use the left side of the thing to set our height. So the first one would have a width of 30 and a height given by the left side of 20. The next one will have a width of 10 and a height given by 30. Next one will also have a width of 10 and a height of 40. Then we'll have a width of 20 and a height of 55. And finally, we'll have a width of 20, I'm going to work up here, and a height of 65. Okay, so kind of going up there. Finally, for some time between 0 and 90 minutes, explain the meaning. Well, remember that r was a rate. Okay, it gave us the rate. So if we're integrating the rate, what we're being given is, I'm going to answer the first question. Let's answer the first question in black. We're being given the amount present after b minutes. Now, next, explain the meaning of 1 over b of the integral from 0 to b. Well, recall that 1 over b makes it an average, and I always just say, so it's the average value of the rate from 0 to b minutes. So that answers that whole free response question. The big thing I wanted to remind you of was getting the slope off a table, but useful to remember the Riemann sums and some of the other things as well. The one other thing I wanted to talk about was how you would estimate a derivative from a graph. And it really goes back to doing the same exact thing we did on the previous slide, which is pick points on either side of it. Now I'm going to try and pick ones that I can easily identify, maybe rather than going whole numbers away. Like I look at this point right here, it's we're going by 0.25, so this looks like 0.75 and 2.5. And the reason I picked that is just for the simple reason that it just is landing on a really nice spot. So that's 1 point. I'm just going to put that in here, right there. It's 0.75, 2.5, that point. Now if I can find another point that's almost as nice, there's not anything that's really perfect. Maybe I'd just go, on the other side, maybe I go to 1.25 and, I don't know, maybe like 1.8 or 1.9. So maybe just pick a point on the other side and kind of estimate it. 1.25, I'm a 1. Maybe 8. Okay. So then, all we need to do is, again, difference in y's over difference in x's. And that's what will estimate the slope, the derivative, at that one specific point. Next, the question on how do you find how do you graph the derivative? The way I always graph the derivative is to start by looking for where the derivative is 0. So I look for the spots where there's a horizontal tangent. So it looks like we have a horizontal tangent right in here, and then I just mark that as a 0 in my derivative. Looks like we'll have a horizontal tangent in here, so I mark that in my derivative. And then I just kind of connect some points. So you see on the left side over here, let's start in between. The slope is negative. The function is decreasing. Therefore, the derivative must be negative. Now, it's not very negative here. It's a small negative slope. Then it gets steeper. Then it levels out. So I'm going to try and express that. It's not very negative. Then it gets more negative. Then it becomes less negative. Okay. Over here, slope starts off slightly positive, then gets very positive. I'll reflect that in my derivative. So can I go up like this? I'm just going to connect the pieces. And finally, on the very left side, we had you can't see much, but slightly positive. So I'm going to make my derivative slightly positive as well.